Here are solutions to homework set number 7 for ECE 463-663 motor control. Now in this homework set, we're trying to control a ball and beam system with a constant disturbance. So the first problem is, let's go back to what we did before, use full state feedback to control the system. To do that, I come up with the dynamics. So here's the A matrix, B matrix, that's from homework set number 4. Linearized at least. Now use full state feedback. So throw that into MATLAB. Here's your A matrix, B matrix. Using pole placement, place the dominant pole at -0.8 and the other pole somewhere out of the way, like 2, 3, and 4. If I do that, I get 4 sets of feedback gains. Find KR to make the DC gain 1, and everything ought to be fine. So to check that, let's try that in MATLAB. So here's your nonlinear simulation. And where's the screen? I've got my feedback control law, KX and KR. 7143. This is going to come up later. I now simulate it. Here's my step input. It just goes from -1 to +1. Here's my control law. Calculate the dynamics, integrate, move forward in time, and here's what she looks like. There it is. Here's what she looks like. So again, I can tell it to go from -1 to +1. It does it. Let's run that again. Here's my step input. Go from 0 to +1. Stable settling time. It's about 5 seconds. No overshoot. Dominant pole's -0.8. Okay, that's exactly what you expect. Now, what happens if there's a constant disturbance? So to do that, I'm going to take the mass of the ball, change it from the nominal 3 kilograms, now make it 2.5 kilograms. What does that do? What that does is I have an extra torque on the beam. Torque is force times distance. If I weigh 0.5 kilograms less, 0.5 kilograms times gravity times your distance is a torque that's wrong. Because I have constant disturbance, I have constant error. That's the problem with what we've been doing so far. It's pretty easy to get constant errors in the system. Basically, KR is chosen as the fudge factor, whatever it takes to make the DC gain 1. If the plant is wrong, the model is wrong, KR is wrong. So how do you avoid that? Well, to avoid that, I can use a servo compensator. What a servo compensator does is it adds an integrator to the output. At steady state, all the states are constants. If Z is a constant, Z dot right here is 0. If Z dot is 0, then Y has to equal reference. Guaranteed it tracks, as long as you're stable. So let's do that. Form the augmented system. So here's your A matrix. There's the servo integrator. Here's the C times B, or BZ times C, and a zeros matrix. Augmented B matrix with respect to U. Augmented B matrix with respect to R. And we'll look at position. Now, I take the augmented system, stabilize it. Here I put the closed loop dominant pole at -0.5, other ones just out of harm's way. You get gains. The first set of gains are times the state X. Last one is times my servo state Z. So here's KX, there's KZ. For the linear system, I can see how it should behave. Form the closed loop system, that's your A minus BK, B with respect to R, C and D. Plot the step response, and it tracks. Settling time is 4/0.5, the dominant pole, about 8 seconds. Okay, looks reasonable. Take the step response with respect to U, and it goes from 0 to 0. So the servo compensator does two things. It tracks a constant set point and rejects a constant disturbance. So let's try that in MATLAB. Try that in the other MATLAB. So here's my graph. Here's my control law. I'm going to go back and change it so that rather than using KX times X, KR times R, I'm going to add the servo compensator, KX and KZ. The servo dynamics is your z dot equals 0 times z, it's an integrator, plus 1 times the difference. And my servo state initially is 0, just what's the initial condition of my integrator. Go into the control law, change it from what we had before to minus kz times z minus kx times x. Add the dynamics for the servo. Integrate the servo compensator. I think that's all. And I should have a system that tracks a constant set point for the nominal case when the mass is 3 kilograms, and when it's 2 kilograms when I have constant disturbance. So let's try the nominal case first. When the mass is 3 kilograms, it doesn't look all that different than what we did in problem number 1. It works for the nominal case just fine. Problem 1 worked in the nominal case just fine. Not a huge difference. Now let's add a constant disturbance. Change the mass of the ball to 2.5 kilograms. And try again. Now when the mass is only 2.5 kilograms, the integrator is searching. What torque do I need to get the ball to 1? It searches, 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 finds out the answer, and forces the error to 0. And that's true in any case, as long as you're stable. Change the mass to 3.5 kilograms. Oops, and you can't run subroutines. Run the main routine. Is now doing a search. What torque do I need? What constant do I need to hold the ball at 1? It figures it out. That's the beauty of servo compensators. They will guarantee track a constant set point regardless of a step disturbance. Okay, the next problem. That works for a step. Does it work for a sine wave? So let's try it. Here is a sine wave input. See what happens. There's my sine wave going back and forth at 0.7 radians per second. And she's trying, but not terribly successfully. The problem with the previous solution is it tracks a constant, but doesn't track a sine wave. If you do want to track a sine wave, I need a different servo compensator. So there we are. If I want to track a sine wave, now use the servo where this has poles at plus minus j 0.7 radians per second. And pick B so that's controllable, 0.7. So, kind of arbitrarily, this is one A matrix that has poles at plus minus j 0.7. There's an infinite number of A matrices that do that. Pick one. Pick BZ so that's controllable. Now when you form the augmented system, here's your A matrix, zeros matrix, B times C, and here's my servo states, the servo dynamics. The B matrix with respect to U, B matrix with respect to C and D. Now, pole placement. Place the closed loop dominant pole so that it's stable, has a settling time of 12 seconds, and put the other poles out of harm's way. If I do that, I get gains. Maybe not the best set of gains, but that's what I got. When I do that, the first 4 gains are Kx. The last 2 are times my dummy state, the servo state. So this is your Kx, and here's your Kz. I can check the linear system, form the closed loop system. In this case, I have to use our step 3 function because MATLAB doesn't have the input to a sine wave input. I have to create one. This is for an arbitrary input. Let's make the initial states 0. So that's a zeros matrix, 6 by 1. I've got 6 states. Here's my closed loop A matrix, the B matrix with respect to R, C, and D, time points, 0. My set point is sine of 0.7t. Plot the step response. The pink line is my set point, the blue line is the output. On paper, it should track. If I change this to the B matrix with respect to U, this is what happens if I have a sinusoidal disturbance, meaning like the ball only weighs 2.5 kilograms. In that case, the disturbance goes to 0. It rejects the sinusoidal disturbance at 0.7 radians per second. So that seemed to work on paper. Let's try it in MATLAB. Let's go over here and change my control law. So now it's the kx, kz that I found for the augmented system with the servo compensator having poles at plus minus j.7. Kz, my servo dynamics, poles at plus minus j.7, the servo's input, whatever makes it controllable, and now the servo has two states. Same as before, my reference is a sine wave. Here's the input, the plant dynamics, the servo dynamics, integrate everybody, plot. And if I try that, here's what she looks like. I'm trying to track a sine wave at 0.7 radians per second, and it nails it with a settling time of 4 over 0.8, whatever that is, 12 seconds. That's for sine wave. Try cosine.